we have learned how to find the HCF and the LCM using multiple methods, prime factorization, common division, or by listing out the factors or the multiples. Now, depending upon the question or depending upon the method mentioned in the question paper, you are supposed to solve them. Now, let us see what are the important points that you can derive from this particular concept. One is obvious one, highest common factor and the lowest common multiple. Let us look at one more important point that we get to understand from this. Let us take the LCM of 24 and let us say 36. Okay. What is the HCF of 24 and 36? The HCF of 24 and 36, I can say that this is 12 into 2 and this is 12 into 3. So the HCF is 12. By some method, suppose you figure out the HCF and you find that it is 12, you can represent 24 as 12 into 2 and 36 as 12 into 3. Now, this is our HCF. One is HCF into 2 and other is HCF into 3. Correct? What can you understand from the remaining number in this particular equation? 24 is this and 36 is 6. You can see that 2 and 3 are co-prime. They do not have any more factors in common. Right? Now let us take another set of numbers. Let us take 4 numbers in this case. Here I have taken 104, 48, 72 and 40 and I am trying to find the HCF by using common division method. When I am doing it, I am dividing first by 2 and then by 4. So this is what I am getting. I can see that there is no more number that is in common for all the 4 numbers. So I leave my division over there. So my HCF is 8. Right? So I can represent 104 as 8 into 13, 48 as 8 into 6, 8 into 9 and 8 into 30 is 240. Which basically means this is HCF into 13, HCF into 6, HCF into 9 and HCF into 30. Correct? What can I say about the remaining numbers? As you can see, all these remaining numbers are co-prime. So from this, we have a very important concept. Suppose we have got unknown numbers that share a common HCF of, let us say, any number 6. Okay. Suppose there are 3 unknown numbers x, y and z that share a common HCF of, let us say, 6. We can immediately represent those numbers as the first number is HCF into, let us say, A. Second number is HCF into B. And third number is HCF into C, where A, B and C are co-prime. So any set of numbers with a given HCF can be represented in terms of HCF and numbers that are co-prime. I have mathematically written down what we just studied. So if you have 3 numbers, number 1 and 2 and 3, which have a common HCF of H, then I can represent the numbers in this way, where X, Y and Z, they are co-primes, they do not have any common factor between themselves. Okay. Now we go to the second point. Suppose these 3 numbers has an LCM of L. What can you say about the LCM L? One thing is that the LCM L will be a multiple of the first number, second number and the third number. Correct? Because LCM is the least common multiple. Because it is a common multiple of these 3 numbers, the LCM has to be divisible by the first number, second number and the third number. Okay. Now, because the LCM is divisible by the first number, second number and the third number, the first number is this, second number is this and the third number is this. Correct? Because LCM is divisible by this, this and this, it obviously means that the LCM has to be divisible by the HCFH and each of these co-primes. Okay. So, whenever we have a set of numbers with a given LCM, that particular LCM should be divisible or will be divisible by the given numbers, which means that LCM will be divisible by the HCF as well as the co-primes. So, that is our second point. We will take an example so that you get a better understanding of the second point. Look at the numbers I have taken, 20, 12 and 8. The HCF of these 3 numbers is 4 and the LCM was found to be 120. Because the HCF was found to be 4, I can split the numbers as 4 into 5, 4 into 3 and 4 into 2. 4 being the HCF and 5, 3, 2 being co-primes. As you can see that the LCM 120 is divisible by the HCF 4 as well as each of the co-primes. Okay. So this is a very easy concept. So I just took an example that which is relatively easier for you to understand also. Now the first 2 points we are done with. So let us move on to the third point. This is our third point. The product of LCM and HCF is equal to the product of the set of numbers involved. One thing you need to remember is that this particular formula is applicable only for a set of 2 numbers. When the number of, like in the sense, suppose the numbers given to you are more than 2, you are dealing with HCF and LCM of 3 numbers or 4 numbers. This formula is not applicable at all. This is applicable only for 2 numbers, suppose 20 and 15, 18 and 20, something like that, but not more than 2 numbers. Okay. So remember this formula because there are many sums that come from this particular formula for in your examination. So LCM into HCF is equal to the product of the 2 numbers that are given to you. Now let us do a few word problems or numericals based on the concept that we have studied so far, including Fundamental Theorem of Arithmetic or LCM, HCF, etc. and see how well you are able to apply this concept to those sums. So we do our first sum. Check whether 6 raised to n can end with 0 for any value of n. Now this is a direct application of the Fundamental Theorem of Arithmetic. According to the theorem, we know that a number can be factorized using prime factors in a unique way. Okay, there is no other prime factor that come into the factorization of a particular number other than the ones that we are finding out. Any number ending with 0 has to be divisible by 2 as well as by 5. Correct? So if it's a 10 or a 20 or a 100, any number ending with a 0 has to be divisible by these 2 numbers. The number 6 is represented by prime factors as 2 raised to 1 into 3 raised to 1. Now 6 raised to n can be written as 2 into 3 the whole raised to n or 2 raised to n into 3 raised to n. Right? Because the Fundamental Theorem of Arithmetic states that the factorization of a number using prime numbers is unique, 2 raised to n into 3 raised to n. This number cannot end with 0 because the factor 5 or the prime number 5 is not involved in the factorization of 6 raised to n. Okay, that is the reason 6 raised to n can never end with a number 0. Here you have our second sum. Check whether 5 raised to 2n can end with 0 for any value of n. Okay, again it's the same concept, I am not going to repeat it. So 5 raised to 2n. What are the factors which are involved in 5 raised to 2n? I can say that it is 5 and 1. 1 is not considered as a prime, so it is only 5. So 5 is the only prime that is involved in the factorization of 5 raised to 2n. Okay, now for any number to end with 0, what is the condition? The condition is that the number should be divisible by 2 as well as by 5. Correct? Now this number is divisible by 5 because 5 is involved in the factorization, but you cannot find 2 here. Therefore 5 raised to 2n will never end with a 0, whatever be the value of n. See, it's the same concept that we applied in the previous sum. Even the statements are almost the same, except that in the earlier case the 5 was not involved in the factorization. In this case 2 is not there in the factorization. Okay. Find the HCF and LCM of 144 and 96 using prime factorization and verify HCF into LCM is equal to the product of 2 numbers. So this is the basic type of sum that can come using this particular formula. In order to do that, 144 and 96, we need to find the HCF and LCM using prime factorization. So for that I have to individually factorize or do the prime factorization of 104 and 96. Okay. After that, after factorizing till I get 1, I have continued with the factorization. Then I have written down the factors or the prime factorization of 144 and 96. And as I told you before, in order to find the HCF, I need to identify the factors which are common for both 144 and 96, which is 2 and 3. I need to take the least power of each factor, which is 2 raised to 4 over here and 3 over here. So I get 48 as a HCF. In order to find the LCM, I will be taking the factors in which the highest power of the numbers. So 2 raised to 5 and 3 raised to 2, I get 288. Now I verify the formula HCF into LCM. So this is my HCF and LCM, I get this. And by multiplying the numbers also, I get 13824. So you can see that this particular formula is valid for the HCF and LCM of these two numbers. Okay. The HCF of two numbers each having 3 digits is 17. The LCM is 714. Find the numbers. Okay. So I have told you whenever there is a set of numbers whose HCF is given to you, we can represent the numbers in terms of HCF and numbers which are coprime. So here we have got two numbers whose HCF is 17. Okay. So the first number I can represent as 17 into x, and the second number I can represent as 17 into y, where x and y are coprime. They do not have any factors in common anymore. Okay. Now the LCM is 714. Find the numbers. You know the relation LCM into HCF is equal to product of two numbers. First number into second number. Now LCM is given as 714 and the HCF is given as 17. This is equal to 17x into 17y. So what do we get? We get x into y is equal to 714 divided by 17. This is 42. Now you have got the product of two coprimes as 42. Okay, so what are the possible numbers that we can have? See, x and y are coprimes according to whatever we have studied so far. Whenever you are representing the numbers in this form, x and y are coprimes. So to give a product of 42, what are the combinations that we can have? One is 1 and 42. Okay, 6 and 7. Now you can have 21 and 2. Our task is to decide which set of numbers actually fit our question. It is given that the numbers are 3-digit numbers. So when we are substituting the values of the three pairs of numbers in 17x and 17y, you can see that the first option 1 and 42 will give me two values, out of which one is a 2-digit and the second is a 3-digit. The values of 6 and 7 will give me two 3-digit numbers, but the third value also will give me one 3-digit and one 2-digit number. So I know that the value of 6 and 7 is the right one here. Before I move on to the next word problem, can we have a short recap of the type of word problems that we discussed so far? One, in the beginning, okay, we learned how to find the HCF and LCM of numbers. We learned how to find the LCM and HCF of decimals. We learned to find the HCF and LCM of fractions. These three are done. We discussed a few word problems wherein you had to figure out whether you should find out the HCF or the LCM. I told you how to figure it out either by elimination or by understanding the sum. Okay. Now after that we did a few sums based on the formula HCF into LCM is equal to product of two numbers. We also learned that whenever a set of numbers is given to you and the HCF is also given to you, those numbers can be represented in terms of HCF and in terms of numbers which are coprimes. So if there are three numbers whose LCM is 15, I can represent the first number as 15 into A, the second number as 15 into B, and the third one as 15 into C, where A, B and C are coprimes. They do not have any factors in common. Clear? Now let us move on to the next part. HCF is also represented as GCD or the greatest common divisor. HCF is the highest common factor or it is also the greatest common divisor. So whenever you have a problem or a sum wherein they are asking you to find the highest common factor of a set of numbers or the greatest number that can divide a set of numbers, you know that you need to find the HCF of those set of numbers. So let us do this particular sum. Find the greatest number that can divide 120, 136 and 118. You need to know that you need to find GCD, which automatically means the HCF. So let us do prime factorization in order to find the GCD of these numbers. Here I have done the prime factorization. I have written down the factors over here. As you can see, 2 is common in all the three numbers. but I have to take the lowest power because I am trying to find the GCD or the HCF. So 2. So that is 2 is the greatest number that can divide all the 3 numbers properly. Okay. Now that you are clear with this particular concept, let us move on to the next one. Find the greatest number that can divide 432, 534 and 398, leaving a remainder of 7 in each case. Now, you have seen similar sums like this, and the answer to this particular question is, anywhere you check, reference book or in any of the websites if you check, the answer to this particular question is, find the HCF of 432 minus 7, 534 minus 7 and 398 minus 7. Correct? Now, this particular sum is not very difficult to understand. You know, a person who is familiar with HCF and LCM can easily understand the concept behind this particular sum. Now, most of the time when students get sums like this, I know there are a couple of sums of different kinds under the same concept. What they do is that they by heart the method in each of the cases and apply it to the sums as and when they come. Now, by hearting this particular type of sums is absolutely okay. The reason being, there are only 3 or 4 types and there are not many sums that can come from those. Hardly 1 or 2 sums can maximum come in your internal examination or in the board examination, not a wide variety of sums. Okay. So, if getting mark is your only consideration, please go ahead and by heart. But if you really want to understand why we are doing this particular step, or if you are not able to understand but you still want to understand why we are doing this particular step, I will explain it to you. We have 3 numbers, 432, 534 and 398. There is a number or the greatest number. So whenever you say greatest number which can divide, you automatically think of HCF. Okay. So these 3 numbers has an HCF. When we divide these numbers by that HCF, what happens? It will leave a remainder of 7 in each case. Now, I will explain it to you mathematically. You know that dividend is equal to divisor into quotient plus remainder. Correct. In the first case, what is the dividend? 432 is equal to, what is our divisor? Our divisor is our HCF into quotient plus our remainder. I have taken Q1 because the quotients will be different for each number. What is 534? Dividend into quotient plus remainder. What is 398? Dividend into quotient plus remainder. So far so good. I am going to take 7 to this side. What do I get? I will get 432 minus 7 is equal to HCF into Q1. 534 minus 7 is equal to HCF into Q2, and 398 minus 7 is equal to HCF into Q3. We got 3 equations. Now, what is it that we need to find? We need to find the HCF. HCF of what? HCF of this set of numbers. That is the reason we are subtracting 7 from this and then find the HCF of that. So from this set of equations, what do you understand? There is an HCF that is associated with these 3 numbers that will actually leave a remainder of 7 from 432, 534 and 398. Okay. Now, I have explained to you why we have used this particular approach. So let us now find the HCF of these 3. This is what we are getting after prime factorization. As you can see, 17 is the only common factor for all the 3 numbers. So 17 is the greatest number that can divide these 3 numbers, leaving a remainder of 7. I hope you are clear with the steps as well as the reason why we have done this particular step of 432 minus 7, 534 minus 7 and 398 minus 7. Okay. Find the greatest number that can divide 2930 and 3250, leaving remainder 7 and 11 in each case. So what is different from the previous sum? The only difference is that the remainders are different in each case. In the first case, it is leaving a remainder of 7. In the second case, it is leaving a remainder of 11. Our basic understanding of the concept is not going to change. So, those who want to by heart the method, when I am writing the method finally, you can please by heart the method. But others, please listen over here. So, dividend is equal to Since it is a greatest number, it is divisor into quotient, a random quotient plus remainder. In the second case, it is dividend is equal to divisor into another quotient plus remainder. Now, 2930 minus 7 is equal to HCF into Q1 and 3250 minus 11 is HCF into Q2. So, from this statement, what can you understand? One number is HCF into Q1, the second number is HCF into Q2. So, if you find the HCF of these two numbers, we will get the value of the number that is asked in the question. Correct? So, we need to go ahead and find out the HCF of these two numbers. So, the answer would be HCF of 2930 minus 7 and 3250 minus 11. Now, let us find out the value for this. The answer for this particular question is 79. I am not going to go into the steps of prime factorization. I have explained it in many sums. So, any set of numbers, whether it be 2 numbers or 3 numbers or 4 numbers, any set of numbers, they have given to you and they have also given the remainders. Either the remainders can be same or the remainders can be different. And they are asking you to find the greatest number that can divide those set of numbers leaving such kind of remainders. You know what to do and why you are using this particular step, and that you have to find the HCF. Okay, suppose you have got 3 numbers, suppose they 35, 42 or 29, and suppose they say they have remainders of 7, 11, 2, something like that. You know that you need to subtract each of them individually and find their HCF, and this is the reason why you are doing it. Find the greatest number that divides 1750 and 2000, leaving remainders of 48 and 2. It is exactly similar to the sum that we did before. So, basically our answer would be, we need to subtract the remainders from the numbers and find their HCF. I hope you are clear with why we have chosen this step and what exactly to do when you are getting a sum like this. I am not going to go into the details or how to do the sum. So, I think you can well do the calculation and find out the answer for this. Find the greatest number that divides 43, 91 and 183, leaving the same remainder in each case. Now, what is the difference between this sum and the previous sums? In this case, the value of the remainder is not given to you. Okay. So, our equation, now before I start with the equation, let me tell you the answer to this one. The answer to this one would be, find the HCF of this. Difference between the respective numbers. Okay. Here I have written our basic equation. Dividend is equal to divisor. It is the greatest number, means it is the highest common factor, or the GCD, greatest common divisor. So, divisor into quotient, a random quotient plus remainder R. Because the value of the remainder is not given to you, I have taken it as a value of R and all the numbers are having the same remainder. So, 91 is equal to this plus R and 43 is equal to this plus R. Now, our problem is there. The reason being because there is an unknown variable which is R. Earlier it was a number, so it was easier. Here we have a number or a variable R whose value we do not know. We can solve this particular set of equations only if the variable R is eliminated. Fine. How do we eliminate a variable R from a set of equations? We do that by subtracting the set of equations from one another. So, let us see what we are getting when I am subtracting the equations. I am going to subtract 1 minus 2, 1 minus 2, 1 minus 3 and 2 minus 3 in order to get 3 sets of equations. So, what are we getting over here? 1 minus 2 is giving me this, 2 minus 3 gives me this and 1 minus 3 is giving me this. Okay. So, 183 minus 91 should give me 92, 48 and 140 for each of these values. So, what do we have here finally? We have got 3 numbers which can be represented in terms of HCF and another set of numbers. So, we immediately know that whenever you have a set of equations which is represented with the help of HCF, we know that these numbers will be coprime. So, in order to solve, what do we need to find? We need to find the HCF of these three numbers, which is actually the difference between the individual numbers. So we come to the answer which you guys automatically by heart when you are doing this particular chapter. Am I clear? First, we wrote the individual equations. Unlike the previous cases, since the remainder r did not have a specific value, we needed to throw away r somehow. For throwing away r from a set of equations, we subtracted each equation, and this is what we are getting. The HCF did not disappear, it is still there, which is represented as HCF into product of a number, HCF into product of a number, and here also. So we immediately know that we need to find the HCF of which numbers? These numbers. Clear? Here I have shortlisted whatever we have studied so far. Dividend is equal to divisor into quotient plus remainder. Based on this particular concept, I have explained to you how the answers have come about in different kinds of sums regarding the HCF. In the first sum, the highest number that exactly divides a set of numbers will obviously be the HCF of numbers. In the second one, the highest number that divides a given set of numbers, leaving a remainder or a different remainder, where the value of the remainder is given to you. Suppose they say a remainder of 7 in each case, or a remainder of 7, 11 and 13 respectively in each case. In those cases, we need to find the HCF of the difference of the number and the respective remainders. In the third one, when the remainder is not given to you, it's an arbitrary remainder, we need to find the HCF of the difference between the numbers. I hope the reason as well as the steps are very clear to you. Now I am going to move on to LCM.